Hi everyone, in this video we will be looking at successive ionization energies. We will look at the raw data and the graphs associated with successive ionization energies, and on doing so we will then proceed to look at how the data provided by these successive ionization energies have been used as evidence for the existence of discrete energy levels, that is, shells or subshells. Let's start by looking at what successive ionization energies are. I have my definition on the left here, where it says successive ionization energies show the amount of energy required to remove all electrons from an element. We are told it generally increases as we remove these successive electrons, and this is because inner electrons experience a greater nuclear charge. We're going to look at the diagram on our right, or the figure, which shows us the element sodium to argon in period 3, and it lists the amount of energy taken for the successive ionization energies, that is, to remove the first 10 electrons from each element. If we look at the data given to us, let's say for example for sodium, we would see on going down or looking at the first 10 successive ionization energies, the general trend is an increase, meaning that as electrons are successively removed from the same element, we are going from the outermost shell to inner shells. This would mean it takes more energy the closer the electron is to the nucleus as it experiences a greater nuclear charge. In this diagram that we see on the screen, it has already been highlighted for you how we analyze the data. So for example, in sodium, we're going to see the first and second ionization energies have been highlighted. It's the second and the third for magnesium, third and fourth for aluminum, and so forth. Now, why are these data more important than looking at the rest? This is because on looking at the difference in ionization energies, that is from first to second, second to third, third to fourth, etc., we would see large jumps in the ionization energy. So let's say we're looking at sodium. The first ionization energy was 496 kilojoules per mole, but the second is 4,560. This is a very large jump compared to it's a very large jump, right? Or one of the large jumps in this element sodium. And there's a significance where we have large jumps in ionization energies. What we are going to do is I'm going to look at one element and we will use that element as a model for the others. Alright, so here we have a table which shows us the successive ionization energies for sodium. What we are going to do is we have to look at the data given to us by looking at the jumps in the ionization energy. That means I'm going to look at the jump from first to second, second to third, third to fourth, etc. So what I'm going to do is I'm going to go ahead and writing what would be the values for these jumps in ionization energies. So what I have done is calculate the jumps in ionization energies, and I've taken the liberty to write out what would be the jump in the ionization energy. So I'm just going to write here on the left the electron which is being removed. So we have the second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and this would be our 11th electron. We're going to look at our data here, and what I'm going to take the liberty to do is to not look at the ionization energies for our 10th and 11th electrons. These have very large jumps, but we would understand that the closer the electron is to the nucleus, the greater the amount of energy required to remove that electron. I want to analyze our data just looking at up to, let's say, this 9th electron being removed, because I want to examine similar data in a similar values, right? And we're going to look at our similar values to look for the largest jump. So our 10th and 11th electrons, of course, are closest to the nucleus. They would require the largest amounts of energy in order to remove them from the element. We are looking at our electrons being removed, and we're looking for a large jump in that ionization energy. We would see a large jump in ionization energy on removing the second electron. Right, so this is 496 to 4563. So this gives us a large jump in ionization energy. What this large jump in ionization energy indicates is an electron being removed from an inner filled electron shell. This should tell me that if it took 496 kilojoules to remove the first electron, and there's a large jump in order to remove the second electron, this electron would be in an inner filled electron shell. So as stated here, the data provided by successive ionization energies allows for the number of electrons in the valence shell, which is a group number, to be determined. So we can see from here that there's one electron in the outer shell of sodium, right? Because the second ionization energy is so large, it means that we are removing electrons from an inner filled electron shell. In looking at our data, we would see that there's a large jump from the first to the second electron. And there's also a very large jump in removing the 10th electron. Right, these two large jumps can also be analyzed, and what it tells us is that in our atom there exists electron shells. Right, so I'm just rewriting what would have been the jump in the energy. Right, so here we have a large jump. Right, this indicates an electron being removed from an inner filled electron shell. Now the data that I am looking at, which is numbers, is a little hard to figure out the jumps in ionization energy, and an easier way to see the jumps in ionization energy would be to look at the log of ionization energy. So I have a graph, a sketch of a graph, which shows us the log of ionization energy versus the number of electrons removed. From this graph, we can more easily see the jumps in ionization energy. So we see a jump in removing the second electron as well as the 10th electron. In looking at this diagram, what it shows us is the existence of electrons in shells. So here we have 1 shell, 2, and 3. As such, I'm just going to summarize by saying that successive ionization energies provide evidence for the existence of discrete energy levels. For examples, shells, where the graph of log of ionization energy versus the number of electrons removed, the large jumps provide evidence for the existence of shells, where we look at elements down a group. It will also show a decrease in ionization energy down a group. These two pieces of evidence are used to support the existence of shells.